Okay, so it's time to start our next session. So welcome back to our physics class. So in the morning session, we done with our electromagnetic waves. Now we will do some questions from electromagnetic waves. We'll just see what are the possible questions or what are the questions previously came from this chapter. And I already told you the number of numerical questions and all is very less. Actually, the reasoning type question and some examples will be given, and based on that one, which type of wave is used, such questions will be more in that one. So we'll see what are the questions already came here. So one by one, we will see the questions. Okay. So the first question, you can see here, the charging current for a capacitor is 0.25 ampere. So the charging current is given as 0.25 ampere.
So you carry on. I'll just check it. You can start.
Okay. Camera at all, no?
I just found the camera. Windows button. Did you all?
Yeah. Okay, so I will continue. We had a small technical problem, that's why. So what we were discussing is we have a capacitor and the capacitor is charging and the current is 0.25 ampere. That is, we have a capacitor. You think about a capacitor like this, and this capacitor we are charging. So we have a current of 0.25 ampere here. So when this current is passing through this one, what is the displacement current across its plates? That is, displacement current will be inside this one. So I think it will be clear for you. That is, if you have a capacitor like this, here we have the conduction current IC, and inside we have the displacement current. Now the question is, if this outside current or the conduction current is 0.25 ampere means, then what will be the displacement current or what will be the current inside this one? That's the question. So it's a very simple, that this is a complete circuit. So whatever current is passing through this one, that same current should pass inside. So I told you in the previous section, here the outside current is IC plus ID, and inside also it is IC plus ID. If you write here, outside we have only conduction current, this value is 0. Inside this conduction current is 0, only this one is there. Meaning is very simple. Here we have a current of 0.25 ampere itself. The current will be same, but that is due to the displacement current, not to the due to the conduction current. So you see here the answer. The displacement current is equal to 0.25 ampere as the charging current is 0. So it just says that displacement current and the charging current will be same. Okay, so this is in the case of charging. Once it is charged, what is the current? Such question also will come later, that we will discuss after this one, because it's a mixture of this displacement current concept and our AC capacitor charging concept. So together we have to apply that one. So I'll go for the next question. See here, this one. A capacitor has been charged by DC source. What is the magnitude of conduction and displacement current when it is fully charged? Here in this case, the difference is you have a capacitor here, and this capacitor is fully charged. So you see here, when capacitor is charging, what happens is the current increases. So first here it is there. So once it is completely charged, then the current will not be there because it's already charged. So you should remember that one. The current passing here is the conduction current, and inside we have displacement current. All these things are possible during the process of charging. Once it is charged, then there is no current. So the question is, a capacitor has been charged by a DC source. What are the magnitude of conduction and displacement current when it is fully charged? So what will be the answer? Once it is fully charged, then it will not conduct. So this one can come along with this chapter, and even in current electricity chapter also this one can come. You have the Kirchhoff rules application or any other circuits. So in that such circuits, if you have a capacitor, and even when the diode comes in the last chapter, there also it will come. So if there is a capacitor in the circuit, in the DC circuit, you should remember that in the capacitor, during charging only a current will pass through that one. When it is completely charged, no current will pass through that one. So generally in the question, it will be there the capacitor is in the steady state. Steady state means it is completely charged. So it takes a very small time only to charge. So after that, it will be steady state. So charging time current will be there. Afterwards, if you disconnect or you make the both terminal to contact directly or through another resistor, that time this charge will come back. Or if you connect this one to another capacitor, you might have done all those things in the capacitor chapter there. So the thing is, during the charging process, current passes through that one. Once it is completely charged, no current will pass through that one. So that is called as a steady state. So in steady state, no current will pass through that one. So in this one, you can say both will be zero. So here they explained all those things based on the equations and all, but the final answer comes is zero only. I is equal to ID is equal to zero. So you have to just remember that one only. In the capacitor, once it is charged, no current will pass through that one. It will just stay as such. It is called as a steady state. So steady state means, you know, there's no change afterward. That's why it's called as steady state. Now we are going to another question. So here you see an EM wave is traveling in a medium, that is electromagnetic wave. Okay, and electromagnetic wave is traveling in a medium. So we have a medium, in that one the electromagnetic wave is traveling in a medium with a velocity v is equal to vi. So you see here the vector v is equal to vi. What is the meaning of that one when you are writing vector v is equal to vi? Its meaning is the wave is moving along direction I, that is along x-axis. So the direction of propagation of the wave is along x-axis. That's why it's called as vi. You remember that one morning we had a diagram, and we about that one we explained that time it was along z-axis. Now this is moving along x-axis. So in that equation we had kz. If you write an equation for this one, it will be kx because it's moving along x-axis. Draw a sketch showing the propagation of the EM wave, indicating the direction of oscillating electric and magnetic fields. So what you have to do is you have to draw that diagram, what we done, this one and this one. So we already know this one is, this direction is, it is propagating along x-axis. So this will be x. So the important point is you have to mark x, y, z and all. And this will be y and this will be z axis. So you'll see that one. Okay. The next, its answer is there in the next page. So you see here, you can see here the propagation, direction of propagation is along x-axis because our velocity was vi. As it is along x-axis only, we given I. So you have to take care of that one. So you, while marking, it should go along x-axis. And after that, the electric field should be perpendicular to that one. So it is along y-axis. The electric field is along this one. And the magnetic field should be perpendicular to both the propagation and the electric field. So all these three will be perpendicular to each other. So we have, in this direction, we have the magnetic field. So you have to remember the electric field, magnetic field, and the direction of propagation. These three should be perpendicular to each other. That's what you have to remember. So this drawing, so it's all actually a, you can see this is a board question only, 2013 board question only, that one. No, sorry, that not that one. This previous one. This one also was a board question only. Delhi 2013 is a board question only. So such questions can come for the board examination. Okay. Now the second part of this one, you see, how are the magnitude of the electrical and magnetic fields are related to the velocity of electromagnetic wave. So that also we discussed the velocity, how the velocity is related. See here, it is C is equal to E naught divided by B naught. So there are some more things are there to discuss. The speed of the wave in vacuum, C is equal to E naught by or E0, maximum value of electric field by magnetic field. One more thing, if you take a particular instant, there if you write C is equal to E by B, then also it is not wrong, okay, because they are in phase. So if when this is maximum, this will be maximum. When this reduces, same ratio, this will reduce. So if the speed of wave C is equal to the maximum value of electric field divided by maximum value of magnetic field, or simply at an instant, if you take C is equal to E by B, that is also correct. It's not wrong. But one thing you should remember, this one is applicable when it is moving in the space. So if it is moving in some other medium, then this will be the speed in that medium. Okay. Now we'll move to the next. This is actually 3 questions I given in a single page. It's actually 3 questions. As it is a very direct and simple question, all the 3 are given together. Actually, it is a different year. One is, you see, All India 2013 question. Another one is Delhi 2012 question, and the other one is All India 2012 question. So this asked in 3 different years. This is a different question paper. It is okay. So it is almost similar, or whatever you know. That's this is already theory part we taken. That's why everything is given together. So the question is, it is the application of electromagnetic waves. Welders wears a special goggles or face mask with a glass window to protect their eyes from electromagnetic radiation. Name the radiation and write their frequency, range of their frequency. That is important. That's why I told you should know in which range which one is coming. So each one range is required. The exact value is not required, at least 10 to the power watt, or whether it is a wavelength means it is nanometer or something. That way you should know. So you know this is UV radiation. So UV radiation is coming after violet. So you know the wavelength of violet, you know. So it is adjacent to that one. So one end you will get, but other end you have to study from where to where the ultraviolet UV radiation is coming. So these welders are using the goggles. Goggles means the glass. Okay, that is to protect their eye from UV radiation only. So this, after this UV radiation, they are asking the range of their frequency. So you have to study the range of the frequency, almost in which range it is coming, that you should take. When frequency range is given, they will be giving concentration to the power, 10 to the power what it is coming. Okay, the exact value, if you write it as 2.3 into 10 to the power something, or 2 into 10 to the power, it doesn't make any difference. But that 10 to the power, that range should be correct. Now, not only this one, just like this one, they can ask, instead of asking this frequency range, give another application of this one. And or as it is UV radiation, something about the ozone also they can ask, or what are its harmful effect, any other. So if you are able to identify this first part, which is that radiation, then only you can answer for the second part only. So that's why this type of question is important. If first itself, instead of UV, if you write IR, this entire thing will go wrong. So you should be careful about that one. So these are the way or the area where you can get easily marks. So that's why you have to give more stress to such chapter. Actually, in the second term also you have some chapters like this related to photoelectric effect, nuclear and all, where you can score good marks. So that there you have to concentrate. Now we'll go to the next question. You see here, name the physical quantity which remains same for microwave. This one was an important. Many times this question came. Name the physical quantity which remains same for microwave of wavelength 1 millimeter and UV radiation. So here 2 values are given. The wavelength of 1 millimeter here and another. When this wavelength is given, people will have a confusion. What is this one? Some calculations is there because this number is given. It is telling that you have to tell a physical quantity of microwave and UV radiation, which is same for this 1 millimeter and this 1600 angstrom unit. So this is given to just to confuse you. Actually, whatever be the value for microwave and for UV radiation, the same thing is its speed. Okay, that is in vacuum, it's already given here. In vacuum, what is same? In vacuum, the speed will not depend on the wavelength. That is, if you take the visible light also, visible light when it is traveling through vacuum, all the wavelength, everything is traveling with the same speed. C is equal to almost 2.99 something. You will write it as 3 into 10 to the power 8. Like that you will write. So speed of light in vacuum is a fixed value. Speed of all electromagnetic waves is same only through vacuum. But when if you take a glass, it's different. If you take when a light is passing through a glass prism, the light bends. It is bending in different way like this. Different colors are bending like this. Why different colors are bending like this? Because its refractive index is different. Refractive index different means its speed is also different. So this speed is different in other medium, but here it is clearly mentioned in vacuum. So in vacuum, for all radiations, if it is visible light or whatever be the all electromagnetic radiation, the speed is same only. So the physical quantity which is maintained as constant or remaining constant for all the waves, that is the speed of the wave or the speed of the electromagnetic wave is constant. So that's the second question's answer. Now you'll see the third question. What is the answer? What are the directions of electric and magnetic field vectors relative to each other and relative to the direction of propagation of electromagnetic waves? This one, previously we done the diagram. In that diagram, what we are telling the same thing only. That is electric field, magnetic field, and the direction of propagation. All these three are mutually perpendicular. That is along x, y, z. Just if you tell it as mutually perpendicular, that's enough. Electric field, magnetic field, and the direction of propagation all will be mutually perpendicular. That's all. So these three questions are very simple question, but still such questions also can come for the examination. That's why it's given. And this can be all these things can come as a single question also, because some 4-mark question and all is there. So in that one, part A, part B, like that also it can come. Okay, now we will go to the next question. Here also, this also, just to know that these types question will come. That's why I included this one. See, identify the part of the electromagnetic spectrum which is, we have two conditions here. Suitable for radar systems used in aircraft navigation. So what was that? This was microwave. For radar, we discussed in this one. This is just theory question only. Suitable for radar system, which is suitable microwave. Why? That also is a question. Why this is suitable? Why radio, comparing with other radio wave, this is more suitable? Because it will 2-3 things is there. Its wavelength is comparatively less with the radio wave, so it will penetrate. Even it can penetrate through the cloud. It will go comparatively straight. Like that, some reasons are there why microwave is used like that. Okay, so you can think of that one comparing with the radio waves. What are the things special for this one? Because when you study diffraction, you will understand that one. The bending also depends on that one. When the wavelength reduces, the bending will be less. Okay, so you can see where the radio waves will bend and come inside this room. The radio will work here, so the microwave will not bend that one. So that's why for radar we are using microwave. So why that is not asked here, but anyway the topic came. That's why we discussed that one. Suitable for radar system used in aircraft navigation. In aircraft navigation means any other navigation also. In aircraft, ship, everywhere it's the same thing only. Now the next part, produced by bombarding metal target by high speed electron. This technical word we not discussed. Okay, that is which radiation is used by or produced by bombarding a metal target by high speed electron. This is actually the mechanism of producing X-ray. So X-ray, we just discussed how X-ray is produced. Means X-ray is produced by X-ray tube. So inside X-ray tube, what is happening? That is this one. So that is, we will use electrons. These electrons will go, and actually some particular setup is there like this. We have here some target, some particular material will be there. These electrons will go and hit this one. When electrons are hitting from here, this X-ray will come out. So that's how it is working in the X-ray tube. So this is X-ray tube. So this is a new thing. You can note on that one. This X-ray means it is bombarding a metal target by high-speed electrons. So the high-speed electron will go and hit that one. From there, electrons are produced. So that's how you'll from there X-ray is produced. That's how you'll produce X-ray. So if like this coming means you should know it is X-ray. That's why I told more and more reading is required, because this is not mentioned in the previous classes. So when question comes, you will see. So when you practice, you will get it. Now one more similar. Name the parts of the electromagnetic spectrum which is suitable for same thing, radar navigation. Same thing, same question. It came in 2 years. That's why radar system used in aircraft navigation. Second one is used to treat muscular strain. This one, with using another word, we explained this one. Used to treat the muscular strain. This is in physiotherapy like that way. That is infrared. IR is used for muscle treatment. So that is for physiotherapy, for relaxing the muscle and all. And the exact biological part we are not going. Just we should know that infrared radiation. You are just giving heat or infrared for the muscles in physiotherapy. So that is also discussed previously. But there we just use the word physiotherapy. Here it is muscular strain means you should know that's a part of physiotherapy. Okay. Then the next one, used as a diagnostic tool in the medicine. This one for diagnosis. You should know in medical field we are using two. We are using X-ray and we are using gamma rays. Both are used in medical field. So X-ray is used as diagnostic tool. That is, we are taking the X-ray photography. If your bones are broken, we are taking X-ray photography. So that's why X-ray is coming there. And the gamma radiation also used in medical field. So how this gamma radiation is used, that also we discussed in the morning session. That is, gamma radiations are used for cancer treatment. For radiation treatment, gamma is used. But here it is clearly given used as diagnostic tool. So for diagnosis, we are using X-ray only. Okay. Now, this is not the complete thing. This may be a 3-mark or 2-mark question because extra is asked. Write the brief how these waves can be produced. Each one how it is produced, microwave, how it is produced. And we already done that table. In that table, it is there how it is produced and how it is detected. So each one, how it is detected. X-ray just now we discussed. And this IR is produced by heat, hot objects, or we even have infrared LED which produces infrared radiation, and this microwave, it is a electronic transition. All those things we discussed. Okay, so this how it is produced is coming as a second part of this one. Now again similar question. Name the following constants of radiation of electromagnetic spectrum, which is, that is same thing only, application. Produce intense heating effect. Which radiation will produce intense heating effect? So the heating effect is produced by which type of radiation? Just now we told the hot objects produce infrared. So this is in 2 ways. Listen carefully. Infrared is related with the heat in 2 ways. One is this infrared, when it is coming and falling a point, there it is becoming hot. That is from sun, the energy is coming to earth as infrared radiation. And in the opposite way also, already one object is hot, that will produce infrared. So infrared means it is actually the heat radiation. So it can be taken in 2 ways. One is the infrared radiation produces heat, or the hot object produces infrared. In both ways you can take it. Next one is the ray which is absorbed by the ozone layer, that we discussed very clearly. That is UV radiation. UV radiation in the atmosphere. So UV radiation is absorbed by the ozone layer. Now the third one, used for studying crystal structure. What is this one? This crystal structure study, that is X-ray diffraction. If you want a very basic idea about that one, means it will be like this. You have the different atoms in the crystal. This is one layer. Okay, for example, you have NaCl crystal or something like that. One layer is this one, and you have another layer here like this. You have another layer. So what happens is this X-ray will come here and it will reflect from here like this. Another layer will go and it will reflect from here. So this one which is going from here, one which is going from here, this is traveling an extra distance. So based on this one here, these two rays will undergo interference, okay, or diffraction. So based on that one, we can find out what is this gap. So for that one, if this gap is d, it is n lambda is equal to 2d sin theta, like that one equation and all. So based on that one, we can find out what is the distance between these two. So that's why it is used for crystal structure. Okay, this part is not required for you. Just I mentioned because you should know how it is used. Okay, for exam and all this will not. Okay, just as a part of general knowledge, I told it is used for crystal structure. Okay, then write one more application of each of these. So what are the one more applications of this one? This is X-ray. So what are one more applications? Infrared, what is the other application? It is used in TV remote, so many other things. UV, also it is absorbed by the ozone layer. It is used for LASIK treatment, and again it is used for purification of water. X-ray, crystal study, another application for medical diagnosis, already done. So all these things can be explained. Now the next question. Which segment of the electromagnetic waves has the highest frequency? That is an important question. How are these waves are produced? So highest frequency, you remember that one like this. We done that one center, visible radiation, ultraviolet, and also that time we discussed one thing. The highest frequency means highest energy. So that was gamma rays. So which segment of electromagnetic waves has the highest frequency? That answer is gamma. And how are these waves produced? How gamma rays are produced? You know, gamma radiations are produced by nuclear reactions. Nuclear reactions also it will produce, and another one is nuclear decay. Decay is also a reaction, but it is naturally happening thing. And nuclear reaction also similarly. Decay means by taking long time it will come. So that is when you study the nuclear chapter, you will understand what it is. Okay. So in nuclear decay or in a nuclear reaction, this is produced. Okay. Give one use of these waves. So what is the use of this one? This is used for cancer treatment. The radiation treatment for cancer, that is this one only. Okay, that's already explained one. Now, next one, which EM wave means electromagnetic wave. Waves lie near the high frequency end of visible part of spectrum. So visible spectrum is there. Here violet is there, and here red is there. High frequency, which is having high frequency, violet is having high frequency. So near to that one, what is coming? That's the question. Waves lies near to the high frequency end of visible part of electromagnetic spectrum. So this is UV. Violet is there. Near to violet means ultraviolet, more than violet. So it is ultraviolet will be there. UV radiation is coming here. So UV is the answer. If you don't know that answer also, the next part you see, then you will get the answer. You see, give one use, let it be there. In what way this component of light has harmful effect on humans? Because the visible light, if you take two sides, one side is infrared, another side is UV. It is telling something about harmful. So harmful is actually ultraviolet only, UV radiation. How UV radiation is harmful? UV radiation, if you are subjected to UV radiation for short time, it can make sunburns. Okay, and that's why if in a very summer, very hot season and all, if you jump in the water in the lake or pond, if you take bath, and that time what happens is you will not feel the temperature because you are jumping in the water. But when you come out, this UV radiation, whatever is coming, that will be absorbed by your skin. But because of this water temperature, you will not feel it. So you will get sunburn. So this sunburn happens because of that one. Not only sunburn, if it is constantly these UV radiations are falling on your skin, it can produce or it can create cancer also. So it is very dangerous actually. For small time means sunburn and all can happen. For more time, it can cause skin cancer also, but still it is useful because it produces the melanin pigment and the human body color. Otherwise, you will be too much white. So the melanin which is required is produced by the light which is falling on our body. And you might have seen for newborn babies, when it is not there, you have to show them to the sun so that when the sunlight falls, the melanin is created. Or for vitamin also, it is required. All those things you might have studied in biology. Okay. Now, which electromagnetic waves lies, that is already okay. And what are the component of light? Okay, in what way this component has harmful effects? That's what we discussed. And this harmful, along with the harmful effect itself, you should remember our ozone layer is protecting us from these harmful effects. Now, next is give one use of each of the following. Already we discussed so many times. Microwave, what is the use? It is used in radar, or again microwave oven it is used. And even microwave is used for communication also, but no need of mentioning because already always we are taking radio waves for the communication. This microwave also is used for some area communications. Okay. Then this ultraviolet UV radiation, what are the uses? That LASIK treatment we done, and after that one purification of water, we use this one, like that. So many uses are there. Then infrared already with the TV remote and the heat radiation, then a night vision camera, and again this satellite picture when you are taking. Gamma radiation also we discussed. It is used for our cancer treatment, everything, so many times told. Okay, but even though we told so many times, you should remember why this one is coming repeated, means many years the same question came. Now this one, this can come like this, or it can come as a part of the other question also. See here, arrange the following electromagnetic radiation in ascending order of their frequencies. That is, we have microwave, we have radio wave, we have X-ray, and we have gamma ray. So the ascending order means the smallest one should come first. So this radio wave will come first. After radio wave, then microwave will come, like that. You should remember whether it is asked ascending order or descending order. First thing is you have to note whether it's asked ascending order or descending order. Second one, you have to check whether it is asked ascending order of frequency or wavelength. Sometimes it will be based on wavelength. Sometimes it will be based on frequency. According to that one, you will be given like this. But always this question will not come like this. It will come in the other way, because many times what happens, they will give some questions. What are the waves used for the following purpose? They will give for purpose. After this for purpose, you have to identify what are the waves. After that, arrange them in the ascending order or descending order will come. So that type also it can come. So that's all. So these almost, I told you, everything is almost similar questions. So these are the questions generally coming from our electromagnetic radiations. Now, now we will move to the next topic, that is ray optics and optical instruments. So now we are moving to the next topic. So this is not question answer. First we will study the theory. After that we will go for the question answers. Study the theory means not that one, but the important area, the direct things you will study. Because you have to, you already, once you've done this one, that's why. Okay, ray optics and optical instruments. So here the first thing is this optics actually, or the when we study about light, we have so many concepts about light. So here this ray optics is actually it's also called as geometrical optics. where we will consider the light as moving in a straight line. Because we can explain many things, how light reflects, how light is undergoing refraction, and how a lens works, how a mirror works. All these things we can explain by considering light as moving in a straight line. So that's why we have the ray optics. And there are some things which we cannot explain if using this ray optics. There we will use wave optics. That is the next chapter actually. That is just like interference, diffraction, polarization. So all these phenomena are actually related to light, but we cannot explain how it is happening. If you consider the light is moving in a straight line just like a ray, then we cannot explain that one. So to explain that one, we will use wave optics. But still there are some phenomena which cannot, just like photoelectric effect. Photoelectric effect, when light falls on particular material, from that one the electrons are coming or the current is coming, that cannot be explained using ray optics, that cannot be explained using wave optics also. So we will consider light as a particle, that quantization, photon and all. So what I want to say here is this, each chapter or each topic is coming to explain something. So the first starting about light is about the ray optics. So here we will consider light as moving as a ray. So what is actually a ray? If you have a point here and another point here, the light is considered to move from this point to here in the straight line path. Actually, it is not 100% a straight line path is correct. The path in which it can reach with the minimum time, the shortest time path. So if 2 points are there, the shortest path is straight line only. Okay, when in a little more higher level, when you are studying, you will understand some area it is different also. Okay, when it will bend also. So here it is moving in the straight line path. So this straight line path in which the light is moving from one point to another, that path is called as the ray of light. So you will get a definition for that ray of light also. That is, light is considered to move in a straight line path from one point to other, and the straight line path is called as ray of light. You might have studied this one in 10th standard also. Now, like this, many rays are there together. This is one ray. Like this, many rays are coming together, then it is called as a beam of light. So we will, whenever we are using the word ray of light and beam of light, that's the difference. Ray of light means it's a single line. And like that, many lines are going together, many rays are going together, a bundle of rays, that is called as beam of light. So we have ray optics. So what is ray optics we discuss, what is ray, what is that also we discuss, and what is a beam of light also we discuss. Now we will move to the actual topics. So here first you will study about the reflection of light. This one you studied in 10th standard. So there is nothing much to explain about this one. So we have laws of reflection once more. Here we have a mirror. In junior class we taken mirror like this. So mirror have two sides, one reflecting side and another side, this back side of the mirror, this is called as the silvered side. So we have a reflecting side and a silvered side. So when light is falling on this one, this is called as the incident ray. The ray which is coming, that is called as incident ray. So the incident ray is falling here and we have a normal here. Don't use the word normal ray. It is not a ray, just a normal there. Okay. So we have a normal here and the angle between the incident ray and the normal, that is called as angle of incidence. And from here it will reflect like this, and this is called as reflected ray, and this is called as angle of reflection R. Now you see here some area will use the word like normal incidence. So what is the meaning of normal incidence? The light is falling perpendicular to this one like this. So when I am using the word perpendicular, I purposefully use that one. The light is falling perpendicular to this one. So what is the angle of incidence? In many cases, people confuses it as angle of incidence as 90 degree. No. When it is falling normally, normal incidence means angle of incidence will be 0. It is perpendicular like this. Okay. So here it is coming and reflecting like this. This is 10th standard you studied, even 8th standard you studied. So this angle of incidence is equal to angle of reflection. That is the first part of our this one, law of reflection. So law of reflection, you have two parts. The first part is angle of incidence is equal to angle of reflection. And we have a second part. What is that? The incident ray, the reflected ray, and the normal at the point of incidence all lie in the same plane. What is the meaning of that one? See here, if this is the incident ray and this is the reflected ray, and if this is the normal, if you have three like these all are in the same plane like this. This one cannot go away from the plane. That's the meaning of that one. Okay. So incident ray, reflected ray, and the normal all lie in the same plane. That's the second part of that one. So we have the law of reflection. Law of reflection and all, it's not a part to study in 12th standard, but it's a basic thing. That's why we discussed that. Now, the next part is about the sign convention. Sign convention also is a 10th standard topic. Still, we will revise that one once. So I see here, a sign convention means actually we have a convention in which we have to take the object this side, image this side should be taken positive, this side should be taken negative. And why it is like that? If you take otherwise, what will happen? Like that, if you ask, nothing will happen. Everything will be right, all the laws, everything will be valid. But the thing is, when we are studying or when you are writing some books, everybody should take in the same notation so that the confusion can be avoided. That's all. Okay, if you take in the other way also, everything will be valid. But the thing is, everybody should take like that. Then only everybody can understand that. That's why on international level, we will have a particular notation. That's all. So the notation what we are using is like that. We have a particular direction like this. And here we will have the mirror. First, we will think about mirror. We have a mirror here, which is kept like this. Okay. Now, when you are keeping the mirror, you take this as the pole of the mirror. Now, just technically the explanation is different, but for easiness, you just take this mirror, this pole of the mirror as the origin of the graph. Then all toward this side is positive, just like the graph sheet. This side is positive, and towards down it is negative. This side is negative, just like x-axis plus x, this is minus x. This is y-axis, this is minus y. Like. But the actual explanation is not like that. The actual thing is, when light is moving from this side to that side, that is, we will always keep the object at this side. That is, the object will be toward the left from here. That is, when we are facing toward that side, toward the left, we will keep the object here. And the incident ray is going this way. So the direction of the incident ray is taken as positive. Okay, it's not from here to there like that. The positive is the direction of the incident ray is positive. So we are from here to here, distance we will not take as positive because the direction of it like that. This distance should be measured from the pole only. All the distance should be measured this side. So we will measure the distance like this, not from here to there. So it will be negative. So the direction of our incident ray is positive, and all the measurement along this x-axis will be measured from the pole. So that will become this side is negative and that side is positive. That is the exact scientific way of telling, but easily remembering is this one. Okay. So it is going like that. We have a situation when we are dealing the Lenz's law in the ray, incident ray is coming opposite direction. That's why you have to take opposite, like that situation will come. So see here, this side is positive, this side is negative. And towards upside, it will be positive, towards down, it will be negative. So what are the things you have to remember? If it is this, the object should be always kept here, and all the measurement toward that side is positive, toward this side it is negative, towards upward positive, towards downward negative. That's all. Now that's a sign convention. When we are using, we will understand that one. Now here one more thing I have to tell. We have mirror formula and Lenz formula, which we already used in 10th standard also. So there people will have a doubt, because when you are doing the derivation of this mirror formula or Lenz formula, we will apply this sign convention once. This side is positive, that side is negative, like that you will do. And afterwards, when you are doing numericals, the focal length is 10 means this it is concave, so you have to take minus 10. So already we in the derivation itself we have taken negative. Why we are taking here? You should not think like that. In derivation you have to take, and when you are doing numerical, again you have to take. Whenever you are taking the value, this side is negative, that side is positive. It doesn't mean that while deriving the equation itself we already done. That's why now it is not required, not like that. While doing derivation also you have to do, and when you are putting the value also you have to do. Whenever you are doing any calculation in optics, this side means negative, that side is positive. That's all. Now we have the focal length of spherical mirrors. This is also simple only. We have the concave mirror here. So this is the reflective. So the rays which is coming parallel to the principal axis will converge to a point on the principal axis. That point is called as the principal focus. Okay. So this is called as a principal focus. Actually, we are discussing about focal length, but this is the principal focus. Here you see here, the rays coming parallel to the principal axis will appear to diverge from a point on the focus, on the principal axis. That is called as the principal focus. So here you see principal focus is that side. So that's why its focal length will be negative. Here it will be positive. So here, when it comes to the lens and mirror, there also you should remember, because whatever happens here for concave mirror, that will happen for convex lens. So you should not think that the focal length also is like that, not like that. This is negative. Concave, whether it is lens or mirror, concave means negative, convex means positive. That's all. Both for lens and mirror. Okay. So the focal length means it is the distance from pole to the focus. You see here, pole to the focus means you have to measure that side. So it will be negative here. Here, pole to the focus is this side. So it will be positive. That's how it becomes positive and negative. Okay, because we have to take all the measurement from pole to that one. So this side will be negative, this side will be positive. And here you see, here we have another word which is called as a focal plane. Because you see here, if it is coming parallel like this, if it is not coming parallel, if it is coming like this, then what it is parallel itself, not parallel to the principal axis. This will come and make an image here. So we have a plane here. That is a plane which is passing through the focus and which is perpendicular to the principal axis. That plane is called as a focal plane. So focal plane means a plane which is passing through the principal focus and it is perpendicular to the principal axis. Such a plane is called as focal plane. That is, focus means just a point. That entire plane, that's called as focal plane. Okay. Now, this is one important thing. That is, 10th standard also we studied this one. What is that? This thing. That is focal length is equal to R by 2. And one important thing you have to remember, this focal length is equal to R by 2 is applicable for concave lens, concave mirror and convex mirror. It is applicable only for mirror. It is not applicable for lens. In the case of lens, this focal length is not R by 2. Why? Because in the case of length, this lens, what happens? The light is going inside this one. The light is coming like this, going inside. So how much it will bend? That depends on the refractive index of that material also. It is not just depending on the radius of curvature. And again, the radius of curvature can be both sides. It will be different. So this F is equal to R by 2 is applicable only to mirrors, not for the lens. And one more thing you should remember, for focal length of mirror, it depends only on this radius of curvature. If whatever be the medium of, or whatever be the material, or whatever be the medium in front, or whatever is there behind, that things will not make any difference. Okay, so this is very important. Focal length is given by R by 2. So how we are getting focal length is R by 2? For that one, we have a derivation, very simple derivation. So that also we'll see here. See here, this is the diagram. Okay, we have a mirror like this, and a ray of light is coming like this, and this is the normal. Normal means always for a circular thing, normal will pass through the center of curvature, and the ray is coming like this. And here angle theta, here also angle theta. This will be theta. This will be 2 theta. It's all geometry. Okay, and here all those things are given there. So you see here from the diagram, if you take tan theta means this is the angle theta. So tan theta will be MD, this one divided by CD. That will be MD by CD. And you know that for small angles, always you will take in such a way that all these lines are paraxial lines. Paraxial lines means what is that? The line which is parallel to the this one principal axis, and it's very close to that one. Okay, so what happens? This angle will be very small. So it will be tan theta is equal to MD by CD. This will be approximately is equal to theta itself. Similarly, for this angle, if you take, you will get tan 2 theta is equal to MD by FD, which is approximately is equal to 2 theta. Okay. Now, if you take these two equations, we can write MD by FD is equal to 2 into MD by CD. Okay. So this MD is common. So from this rearrange, you will get FD is equal to CD by 2. See here, this D is a point here. This is not pole. But as we told this, when you take this entire structure, this will be very close. So D and P can be taken as same thing. So what we can write from this one, this FD means focal length. F will be is equal to CD. CD will be same as C to P. So that will be R, or it will be R by 2. F is equal to R by 2. So this one we done for a concave mirror. Now what about a convex mirror? If it is a convex mirror, the diagram will change. But all this, whatever we written here, it will be same. For concave mirror and convex mirror, these steps will be same. Only the diagram will change. Even this MD, FD, everything is same only. So you have to draw this diagram and you have to write this one. So you should be careful in the question paper whether it is mentioned. You do it for a concave mirror or a convex mirror. For both, you can do the same thing. Only according to the question, you have to draw the diagram. That's all. Now we'll move to the next one. The mirror equation. This one also is similar to that one. Only we'll go a little bit fast for this one because it's just a simple derivation. Most of you may be knowing it. So here what we are doing is first you will draw the diagram. That is, you have a mirror like this and our object is kept here. One ray is going like this and passing like this. Another ray is going like this, passing like this, and the third ray is going like this. So all the three will come here. So the image is formed here. So our AB will be the object and A dash, B dash will be the image. Now we have to take this. I will tell it a little bit fast. So we have to take these two triangles. That is, here we have a triangle and here we have another triangle. These two triangles, these two, that two triangles will be similar. I think you understood what are the triangles. One is this triangle, another is this big triangle. Okay, these two will be similar triangles. So the corresponding sides of the similar triangle, if you take, you will get this equation. Now you have to take again two more similar triangles. That is this big triangle and this much this triangle. That also, if you take, you can write again this one also. So you'll get two equations by taking two sets of similar triangles. Once you will take like this cross triangles, and another one, this one and this one you will take. So you'll get two equations there. Then again, that two equations you have to combine. So you will get this one. Here, one more thing, a small thing is there. That is, this total length is this length plus this length, or this small length is this total minus this one. Like that you have to take. I'm not going into the details of that one. And after that, this U, V, all those things you have to substitute so that you will get our equation. So the details we are not going there. Okay, so finally you will get the mirror equation 1 by V plus 1 by U is equal to 1 by F. So you will get this equation. This is called as a mirror equation. Derivation we are not stressing on that one because of the time constraint. 1 by V plus 1 by U is equal to 1 by F you will get here. This is called as the mirror formula. Okay, now in this mirror formula, you should remember this is applicable for both concave and convex. Mirror formula is applicable for both concave and convex. And one more thing, in this one, when you are doing numerical problem, no need of converting into meter and all. If it is centimeter, everything will be in centimeter. You can do it. That's all. No need of converting into meter and all. Okay, because everywhere, if centimeter means everywhere the centimeter will come. If meter means everywhere meter will come. Make sure that you are not mixing up with the centimeter and meter together. Now we'll go to the refraction part. So in the case of refraction also, we have law of refraction. So what is law of refraction? that just like law of reflection, we have two parts for law of refraction. So the first part is same as the second part of the law of reflection. What was the second part of law of reflection? Incident ray, reflected ray, and the normal at the point of incidence all lie in the same plane. Here also same only, but not reflected, refracted. That is incident ray, refracted ray, and the normal at the interface all lie in the same plane. That's the first part. And we have a second part. So what is the second part? Second part is the sign of angle of incidence and the sign of angle of refraction. If you take that ratio is a constant, that is sin I by sin R is a constant. This is the second part. This constant is called as refractive index. Sin I by sin R is equal to N21. What is N21 means? Refractive index of second medium with respect to first medium. This 2-1 or 1-2 when you are writing, generally people used to take it as very light. So you should not take that much lightly. That is little bit important. So refractive index of second medium with respect to first medium, that is given by sin I by sin R. And you know this one, 10th standard is studied. This equation is called as Snell's law. Sin I by sin R is equal to N21. What is N21 means in terms of absolute refractive index? It is N2 by N1. Those who forgot the 10th standard parts, you just once more remember that one. So refractive index is N is equal to C by V. Okay, if it is N1 or N2, if you this is simply if you use the word refractive index, it's called as absolute refractive index. That is, we are comparing with the vacuum, the speed of light in vacuum divided by speed of light in medium. So if you write N1, N1 will be C by V1. So whether it is V by C, then like that, if you have confusion, you should know the refractive index will be more than 1. So in the numerator, you should get a bigger value. The speed of light will be bigger than speed of light in any other medium. So it will be C by V. Now if you have N2, another medium, then it will be C by V2. Now you see here, when you write N21, very important, N21 will be V1 by V2. N21 is V1 by V2. But when you take in terms of N, N21 will be N2 by N1. I think you understood what I'm telling. That is, when you take N21 in terms of velocity, that is V1 by V2. When you take in terms of refractive index, N21 is equal to N2 by N1. Okay. Or another usually used one is N21 is equal to 1 by N12. So all these things you will use. Okay, this one I'm just telling, not in the order, because you already studied all these things in 10th standard. Okay, now we will come to our point. This one. What is this one? This is refraction of light through a glass slab. And before that one, what is actually this refraction? So generally people will have a idea, common man using, when light is moving from one medium to another medium, the speed of light will change. That is called as refraction. When light is moving from one medium to another medium, the speed of light will change. That is refraction. But actually, when we are using the word refraction, when light is moving from one medium to another medium, it will bend. That bending is called as refraction. Because sometimes question used to come, for what angle of incidence refraction will not take place? That is, if you have a glass like this, if a ray of light is falling directly like this, it will go straight. So what happens is when it is going normal incidence, when it's coming straight, it will go inside also straight. So what happens? No refraction takes place here. No refraction takes place doesn't mean that here speed of the light is not changing like that. Speed of the light is changing, but no refraction takes place means it's not bending. Okay, so for normal incidence, there will not be any bending, but still the speed of light will change. Okay, it will not bend, that's all. So when the light is moving from one medium to another medium, the bending and all, I think you know that with 10th standard you already studied. When it's coming from rarer medium to denser medium, it will bend. Rarer to denser means it will bend towards the normal. Denser to rarer means it will bend away from the normal, all those things. So here in the glass slab, when it is passing through the glass slab, we have something called as lateral shift. That's also 10th standard topic. So this lateral shift means it will get shifted from the initial path for a small distance. That shifting, lateral shift, depends on what? The thickness of the glass slab, angle of incidence, material of the glass slab, all those such things. So that's also 10th standard topic. Here, this is not 10th standard topic. This is new topic. That is, you think that you have a particular dot here, and I am keeping a glass slab here like this. Now, if I look from the top of this one, the light coming from here, it will bend like this. So when it is bending, what will happen? You will feel it is coming from here. So this is the actual depth, and this is called as apparent depth. Now the ratio of this actual depth and the apparent depth, that is the refractive index of this glass. That is, the actual depth divided by apparent depth will be the refractive index of this one. This is not always glass. If you take a coin or an object which is inside a bucket of water or inside a pond, everywhere we will feel it as raised up. So there is a bending, the light is bending here. That's why we are feeling like that. Okay. So this is also a method to find the refractive index of a liquid. Okay, so how much it is raised up? Based on that one, you can find out. So what is the equation for that one? Actual depth or the real depth divided by apparent depth will give the refractive index. This one having another application also that we will study when we are doing the numerical problems. For example, here if you keep a small bulb, this bulb the light will spread like this. Or if a fish is here, when the fish is looking up, what will happen? This fish can see more area than what we are expecting. That's why in a camera and all we have fish eye view. It is showing more area. So that's why it is showing more like this. Okay, that's about this apparent depth. So what you should know is the real depth divided by apparent depth will be the refractive index. But when you get to the numerical questions, you should take this real depth and apparent depth correct. Because sometimes it will be given you have a water tank of 3 meter depth. One object is kept there, and when you are looking at the object appears to be raised up by 1 meter. So you should not take that 1 meter as the apparent depth. You are feeling it as raised up by 1 meter. So already 3 meter was there, raised up by 1 meter. So the remaining 2 meter, that is the apparent depth. So the real depth divided by apparent depth will give the refractive index. Okay, that's a simple calculation. Now the next topic, this is one important topic which you never heard. We are starting from here. You never heard means 12th standard. You might have studied if those who studied already once. In 10th and all you not studied. Okay, so we'll discuss about this total internal reflection. Okay, so we'll come to total internal reflection. See here, first we'll start from the beginning. You think about a glass slab like this. Okay, so this is a glass slab. Here this is denser, and this is a rarer medium. Outside is rarer medium, denser medium is here. Now you see here, if a ray of light is going like this is angle of incidence I. Then what will happen? This is denser medium and this is rarer medium. Just now we discussed when light is moving from a denser medium to rarer medium, it will bend away from the normal. So the straight line path was like this. It will bend away from the normal like that. So this is I, this is R. I think this concept is clear. That is, when it is coming from a denser medium to rarer medium, it will bend away from the normal. Now, if this angle of incidence is increased a little bit, what will happen? It will come some more closer to this one. And if you increase some more, what will happen? It will go parallel to the surface like this. So that angle of incidence for which the angle of refraction is 90 degree, that is called as critical angle. Once more, the angle of incidence for which, this I will write it as IC, the angle of incidence for which angle of refraction is 90 degree, that is called as critical angle. So I think the concept of critical angle is clear for everybody. The angle of incidence for which the angle of refraction is 90 degree, that is called as critical angle. When it will happen? When the light is moving from denser to rarer, then only it will happen. From here to here, that such a critical angle concept is not there. The critical angle is applicable when the light is moving from denser medium to rarer medium. So this diagram is same as this one. Okay. So once more, you see here, when the light is moving from here to here, see what happens? One part of that one is going like this, and the other part is getting internally reflected. Here also reflection is there, that I not done, that's all. Okay. So one part is going there, another part is getting back reflected here. Now you see here, we are little bit shifting to this side. When you shift here, what happens? The angle increases, then also same thing happens. Again, some more shifting. So we are reaching to the critical angle so that the light ray will move like this. So this angle is called as critical angle. That is the angle of incidence for which angle of refraction is 90 degree. That is called as critical angle. Now the next thing is coming here, that is most important. That is the total internal reflection, or TIR. If the angle of incidence is more than critical angle, then refraction will not take place. If the angle of incidence is more than critical angle, that is, you have the light like this falling here, and this angle of incidence is I is greater than critical angle of the material, then what will happen? No refraction will take place, only it will reflect inside. This is called as total internal reflection. So here, first you have to explain what is total internal reflection. Second thing is, you should know what are the conditions for total internal reflection. So first we will think about what is critical angle. So what is critical angle? The angle of incidence for which angle of refraction is 90 degree, that is called as critical angle. Now, what is total internal reflection? When the angle of incidence is more than critical angle, no refraction will take place. The entire light will reflect back to the same medium. That is called as total internal reflection. Once more, when the angle of incidence is more than critical angle, no light will refract, or refraction will not take place. The entire light will reflect back to the same medium. That is called as total internal reflection. Clear? Now, generally for examination, the question is asked in the other way. What are the conditions for total internal reflection? So we have two conditions for total internal reflection. The first condition is the light should try to pass from denser medium to rarer medium. That's the first condition. The light should try to pass from denser medium to rarer medium. That's the first condition. And what is the second condition? The angle of incidence should be greater than critical angle. So we have two conditions. First condition is the light should try to pass from denser medium to rarer medium. Second condition is the angle of incidence should be greater than critical angle. If these two conditions are satisfied, no refraction will take place. The entire light will reflect back to the denser medium itself. So that is called as total internal reflection. This total internal reflection is having so much importance. It is applied in many, many places. And even if you are seeing me through internet, means you are able to see me because of the total internal reflection. Because our communication data, entire data is passing through the optical fiber communication. So optical fiber is working based on this total internal reflection. Throughout the country or throughout the world, the internet is working through the optical fibers. The optical fibers are working based on total internal reflection. Now, there are some other simple examples of total internal reflection also. Here, what is given here, this is actually in your textbook, such diagrams are there. These are the ways in which we can do demonstration of total internal reflection. You see here, this is actually something like a beaker. So here you can send a laser light like this. When you send laser, the light will go like this and one part will reflect like this. Now you can change the angle of laser like this. When you change the angle, when it is crossing the critical angle, you can see that it will reflect like this. This will not go. That is one example. This is in a test tube. In a test tube, if you send light like this, you can see it will reflect like this. If it's a long tube, means it will continuously reflect like this. It will go like this inside. So that's also an example of total internal reflection. And another very simple reasoning type thing is, you might have seen in some soft drinks, the carbonated soft drinks, which is colorless, like 7-Up, Sprite, such things. Even at least in their advertisements, that small bubbles which is coming in that one, that will have a silver color. That will be something shining like a silver color. So for that one, the reason is that one only, because we have, when a bubble is there inside a water, you can see the outside water will be denser medium and that bubble will be rarer medium. So when the light is trying to pass from this water to that bubble, from denser medium to rarer medium, what will happen? Total internal reflection will happen. So this entire light will reflect back so that we will feel it as silver color. So many examples are there like that. Okay, actually, in the new textbooks, some examples and some natural phenomena related to that one is removed. Still, we will discuss that one. So this is some simple examples, or we can call it as the technological application. Actually, we had two parts. One is the natural examples of that one and the technological. So now we have the technological thing, and the natural examples, actually it is not mentioned here. Natural examples means the simplest example what you can say is diamond. So we know that for diamond, we will use the word brilliance of the diamond. The diamond will be shining like anything. So why the diamond is shining like that? This diamond is having a very high refractive index. So when the refractive index is very high, the critical angle will be less. Actually, we not discussed that one. So I will just 1 second, we will go back and do that one also. So here we have a relation between these two, critical angle and this one. So you know this sin I by sin R is equal to refractive index. Okay, N21. Now in this at a critical angle, how it will be? At a critical angle, what we can write? Sin IC, this sin R will be sin 90, which will be 1. Sin IC is equal to N21. So this is the relation. So the critical angle IC will be equal to sin inverse of N21. So the critical angle is given by sin IC is equal to sin inverse of N21, or sin IC is equal to N21. But when you are doing the numerical problem, it makes a problem. See, sin IC is equal to N21 means just if you opposite, you can take IC is equal to sin inverse of N2. So if a question comes like the refractive index of diamond is 2.4, what is the critical angle of the diamond? So directly, if you apply IC is equal to sin inverse of 2.4, that won't work, because sin inverse of 2.4, such a thing is not there, because sin value can go up to 1 only. This 2.4 will not come there. Why that difference comes here? See here, this refractive index of N21, that is second medium with respect to first medium. Here you see this denser medium is first medium, second medium is air. So when refractive index of diamond, when you are discussing, diamond is the first medium and air is the second medium. So here the equation you have to change for that one. So IC is equal to sin inverse of N21. Actually, we need N12, 1 by N12. like this here. You have to take 1 by of that one. Otherwise, so when you take the refractive index of diamond, then 1 by 2.4 you take, its sine inverse you take. Then only you will get. Okay, that people used to make mistake in that one. That's why I stressed on that one. So we have a equation I is equal to sine inverse n21 or I is equal to sine inverse n12. So generally we have to calculate n12. So that's why 1 by we have to take. Okay, so most of the cases the outside will be air or vacuum and inside we have a diamond or glass or something. So the critical angle depends on the refractive index. So when the refractive index is high, the critical angle will be less. So in the case of diamond, what will happen? The diamond, the refractive index is very high. That's why critical angle will be very less. When the critical angle is less, what will happen? Total internal reflection will take place. So when a light ray is entering inside the diamond, what will happen? Critical angle is very small. So that many total internal reflection will take place. And the light will come out of unexpected side. So the cutting of the diamond also is done in such a way that all the light will come through the face where you are seeing, so that you will feel it as shining or brilliant. So that's why if you take any other material and cut in the shape of a diamond, glass and all, it will not have the same shining of the diamond. Only diamond will have that one, because no other material is having the refractive index of diamond. All other glass and all 1.5 and only will come. This 2.4 will not come. Even 1.7, 1.8 and will come. No material is there which is having this 2.4. Only diamond is there. So that's why diamond is having that much brilliance. Now we'll go to our this one. So these are actually applications of total internal reflection. Here we have 3 triangles. So this is actually, these triangles are actually prism. We are making use of this prism to bend the light in different optical instruments, actually in cameras and in reflectors and in telescopes and all. We will use this type of prism to bend the light. Where there is a simple question, why you are using prism? You can use a mirror also. But in the case of mirror, the problem is mirror will absorb little bit light. So much issues are there. This is total internal reflection. The entire light will reflect back. That's why we are using this one. So if you want to bend the light by an angle of 90 degree, we'll use this one. That is, your light is going like this. You want to bend it 90 degree. So you keep a prism here like this. This angle is 45 degree. So it will go like this. And from here, it will undergo total internal reflection like this. And another ray will go like this. This also will undergo total internal reflection like this. So it bends like this. So 90 degree bending is happening. Make sure that this will happen when this angle is more than the critical angle only. Otherwise, it will go. So we have numerical problems based on that one, whether it will go straight like this or whether it will go through this one or whether it will pass through that one. That depends on the refractive index also. But here 45 degree is there and this will bend. So the refractive index will be more. That's why. So if you want to turn the light by 90 degree, we have to use this one. Now, if you want to reflect the light back, we'll use it like this. This one, I think it will be visible for you. If you use it like this, the light will reflect like this and come back, so that the light is coming back. Okay, we can say it is turning by 180 degree. This is familiar to you, this type of reflection. You may not remember it fast. This is used in the case of reflectors. If you see the broken pieces of vehicle's lamp, you will see small triangles like this, or the roadside reflectors and all. This side will be plain, and this side, the back side of the reflectors, the vehicles or the cycle reflector lamp and all. Small triangles will be there. So that when the light is coming like this, each triangle will reflect like this. That's how the reflectors works. So that is this one. Okay. Now, if you want to invert this one, if you have a normal telescope, in the case of a astronomical, that's the difference between a terrestrial telescope and a astronomical telescope. In the case of a astronomical telescope, we have 2 lenses. You are studying in this chapter how the astronomical telescope. So the image will be inverted. So if you have a distant star, when you look at the star, if the star is seen inverted, then there is nothing wrong in that one. But when you are using a terrestrial telescope, when you are looking at an image, it should not be inverted, it should be erect. So we will keep a prism like this. You don't think it as four side. This is actually, if you take it like this, the prism only. So we will use this one to reflect. So the object was here like this. Now it came opposite like this here. So to invert the image also, we will use this one. Okay, this is two applications of, three applications of this prism for changing 90 degree, 180 degree and inverting the image. Now after this one, we will go to the optical fiber. So we use the OFC. That is the, in modern world, that is the most important application of total internal reflection. So here the picture is given. Once more I will draw. So here you see the optical fiber means it is having two parts. This is shaded here. Actually, it will be transparent part. So inside of this one, we have a high refractive index. It may be visible. This inside of this fiber, it will be having high refractive index. That is called as a core of the fiber. So for optical fiber, we have a center part that is called as the core of the fiber, which is of high refractive index. And here outside we have another part. This is called as the cladding of the fiber. This is called as cladding. So optical fiber, we have two materials. These two materials also transparent only, but they have different refractive index. And the inside we have a higher refractive index material that is called as the core, and outside we have a lower refractive index material that is called as the cladding. So our optical fiber is like this. You have a pipe-like structure like this, and this is the core and this is the cladding. Now what happens is when light comes like this, you know this is having high refractive index. This is denser and this is rarer. So this angle is more than critical angle. So it will undergo total internal reflection and it will come like this. Here also same thing will happen. So it will bend and go like this. You can see here the light is bending and going through this one. So whatever be the shape of this one, if you keep it as a roll, if you keep it with bend, whatever is there, if you send light from one side, just it can be called as a light pipe. From here to that side, the light will go. So that is called as a optical fiber. So in optical fiber, the specialty of optical fiber is if you send light from one side, if you keep it straight or bend or circle, whatever, it will go and it will reach the other side. Now, how it is important for communication, this optical fiber? Now, in modern digital communication, what we are doing is whatever value or whatever data is there, that data will be converted into optical signal. That is light signal. And that light signal is transmitted through this optical fiber. So the other end, we have a receiver. So the data can be transferred through the optical fiber. So more data can be transferred. Okay. So that's why this optical fiber communication is very much effective. Okay. So why this optical fiber communication is more, or what is the advantage of the optical fiber communication compared with the normal wire? So generally people used to write the current goes fast like that. Current will not go fast. Here it is light, there it is current. And here we have a high refractive index medium. So it will go a bit slowly. Actually, it is not measurable slow, very minute. So actually the difference or the advantages of optical fiber is the most important, the first one is when current is passing through a wire, we have something called as resistance of the wire. So if you have to take a 200 kilometer, for each 4 kilometer or 5 kilometer, the strength will reduce. So that we have to use an amplifier because of this resistance of the wire. Here you see we are sending through a this one glass, and there is no resistance for that one. So the resistance factor will not come. And one more thing is when current is passing through a wire, if you have external electric field, magnetic field, it can affect that one. Or you have something called as crosstalk. That is signal from one wire can go to the other wire because of the induction. But here such issues are not there. There is no induction. There is no shock. The external electric field and magnetic field will not affect. So very smoothly this will go. And one more, we already discussed the frequency in the previous chapter. The frequency of light is very high comparing with the radio waves or the other waves. So this light when you are sending, we can divide it into big frequency range is there. So we can divide it and give to different people. So the lakhs of people can communicate through a single fiber, or hundreds of people can, hundreds of states or country, city can communicate to a small fiber. So that's why the optical fiber is very, very important in the communication system. And this optical fiber works based on our total internal reflection. For optical fiber, we have two parts, one core which is of higher refractive index and a cladding which is of lower refractive index. When light is going here, it will undergo multiple total internal reflection and it will reach to the final destination. I think this is clear. So once more, total internal reflection is very, very important, and the application of total internal reflection also is very important. And in that one, we have this prism. Already we discussed about the diamond also, and this prism, how it is going, and this one. And you can get some questions. Already I prepared the questions. We'll see it later. If you have a prism like this, and if the light is coming like this, whether it will pass through this one or it will pass through this side, or whether it will go inside this one, all those things, calculations are there that we have to find out. And previously we done that something like that apparent depth and all. So that way also it can happen. If a source of light is there inside the water, that also can undergo total internal reflection. Based on that one also, some questions are there. Okay, that also we will do later. So now for time being, we will stop it now because our time is up now. The next topic in the next session we will do. Okay, because next one, if you start, we cannot complete it before time. So we will stop it now. And 6:30 we'll see. We will continue this one and we will do problems on this one, 6:30 to 8. Thank you. We'll wind up now.